Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resource Center here at the University of Colorado in Denver, and today we're going to talk about our last video associated with periodic waves, simple harmonic motion, this type of thing. So this is the last concept video. There's been 3, so make sure you watch those other 2 because these are based off those other 2. Let's get going because there's a lot to talk about here. So we never really mentioned it in the previous videos, but the idea here that we've been talking about throughout the chapter is this idea of periodic waves. And periodic waves is just a short way to say to talk about a wave pattern, a repeated wave pattern. So when we graph simple harmonic motion with a pendulum or with the spring, we were getting periodic waves. The displacement, velocity, and acceleration graphs were periodic waves that we were forming there. And so there's different types of periodic waves that we can talk about. A certain type of periodic wave is what we call a harmonic wave, which are a type of periodic wave where every point moves with simple harmonic motion, which is where force is equal to displacement. There's no friction or anything, and basically when that occurs, the wave, the harmonic wave, it has the same oscillates with the same amplitude and the same frequency forever, right? And some examples of harmonic waves are electromagnetic waves, waves on a string, waves in a pipe. Those are different types of physical harmonic waves that we can talk about. So everything we're going to talk about here can describe those types of waves. Now, in previous videos, we've talked about velocity, how velocity relates to simple harmonic motion and the acceleration due to that change in velocity we talked about in previous videos, which are right here. But in this section, and I could have introduced it in the last video, but in this section, as there's a little bit more room, we have a lot of different ways to talk about not just velocity, but omega, and not just omega, but k, which is now what we call the wave number. So I just wrote them up all on here. They're just different equations that relate to the different values, right? V is velocity, lambda is wavelength, t is period. So every time you see t, that's period, right? Every time you see v, that's velocity of the wave. And literally, velocity is meters per second. So the units for velocity, meters per second. We could tell you, hey, the wave's moving at 3 meters per second. That's what the velocity would be, right? Frequency would be measured in hertz, right? We tell you 100 hertz, right? And frequency is directly related to omega, or we know omega is called angular frequency in these chapters, right? And then k is not a spring. I know you've known it as a spring constant, but really what we know it as is a wave number. And there's a lot of different ways to solve for k. If you know omega, you can do omega over the speed of the velocity or speed of the wave. That'll get you k. K can also be the frequency over 2 pi frequency over, because that's what omega is, right? Over the speed of the wave. So these are the same equation, just writing omega, right, differently. Or we can also get the wave number by looking at 2 pi divided by lambda, or the wavelength of the wave. So you're going to need how to know how to get those values, and they're also on your equation sheet when you're going to fill in these equations, all right? So anytime we give you a moving wave, we might tell you, okay, here's a wave, it's moving to the right. We'll give you a graph, right, where the wave is going to have a certain amplitude. Like this wave, we'll say is moving to the right there. This wave has a certain amplitude, right? They might say, okay, well, here's a graph of the wave. They'll give you the wave. They're going to have a number for right up here for the maximum, whatever. We'll just call it 10, so that would be the max amplitude for that wave. For example, they would say, okay, well, you have a wave that's moving to the left, right, with at 3 meters per second, with an oscillating or has a frequency of 300 hertz. So they would tell you something like that, and they would say, give us the equation for that wave. So that's what this is doing here. So when we want to write an equation for a moving wave, right, a moving harmonic wave, which again, those velocity, displacement, and acceleration graphs, those waves weren't moving. They were just showing us an example of a periodic wave, repeating pattern wave. But a moving wave is actually a moving wave, like a wave that starts at one end and moves to the other. Like if you have a string and you flick the string, you create a wave, right? And that wave moves through the string. And so that's what we consider a moving wave. And if I keep oscillating the rope, right, I'm going to keep creating a wave that keeps moving through the rope, and it'll move away from my hand. My hand's the driving force there, right? So I give the rope some energy. That rope has some energy in terms of the wave, and that wave moves throughout, or that energy moves throughout the rope. So if we want to describe that moving wave, how a wave's moving this way, or how a wave's moving this way, this is the equation to do it, right? Based off of, and again, I know you know a lot of this stuff, right? Based off of, you know, sine or cosine. So if we give you the wave like this, starting like this, you better write this equation with cosine. But if we give you the wave like this, you better write it with sine. And again, we would give you this information. I know this seems very blank, or it doesn't seem like to have much content, but and the reason why is because we don't ask you to derive these equations. Trust me, there's a way to derive these. All we want you to know is how to use them. Okay, so this is the equation, the blank equation, right, for sine and cosine of how to write an equation for a moving wave. So you already have the blank version. This is the template for a moving wave. Now, if it's a cosine wave, right, if we give you in the question a wave that starts like that, this is the template that you use. If it's a sine wave, something like this is the template you use, again, for a moving wave, all right? And then once you've determined if it's a sine or cosine wave, right, then you want to fill in this part of the equation appropriately. Now, since this is a function of x or t, we know no matter which way it's written, x and t won't have any numbers in it. Okay, so when we ask you to write this equation, if we give you a graph that has a certain amplitude on it, we tell you it's moving with a certain frequency, or the wave has a certain frequency and moving with a certain speed, you can get omega and k from these equations up here. So what you need to do is, when we ask you to write an equation for a wave, A, the amplitude, needs to have a number, omega needs to have a number, and k needs to have a number. X and t, since either one of these templates is a function of x and t, they don't get numbers in here when you give us an equation for a certain wave, because they're going to function on x and t. So when you give us an equation for a wave, if we ask you to do that, A needs to have a number, the amplitude. What will be the number? Whatever it is right here. That's a number. That's the max amplitude, okay? Omega will be related to the frequency. We'll probably tell you the hertz of frequency. Well, if you know the frequency, you can find omega, right? Does that make sense? You just multiply that frequency times 2 pi. You get omega, right? And if you need k, and you know you already know omega. If you know frequency, you know omega. If we tell you the speed of the wave, you can get k and get the number for k, okay? So make sure, no matter which template you use, the amplitude, which is what A is, this is amplitude, okay? Amplitude, omega, which is angular frequency, and k, which is the wave number, those need to all have numbers when you give us the equation. X and t don't. I have a video that shows you how to use this equation, okay? So after this, go watch it. I worked through a couple problems and show you what I'm talking about right now, okay? So how you use those. Do keep in mind, though, that these equations can be written with either a plus or a minus sign in between these two terms. So how do you know how to give it a plus or minus? Well, if we tell you the wave is moving to the right, x is going to be negative. So that means you would make this a negative sign in either one of these, because cosine or sine doesn't matter. What we tell you is the wave's moving to the right. So no matter if it's a sine or cosine function, the wave's moving to the right, this in here needs to be negative, okay? If we tell you the wave's moving to the left, okay, then this sign in here, no matter if it's a sine or cosine wave, needs to be positive, okay? So that's how you determine the sign in here, and the numbers can you can get these numbers in here, k or omega, based off the relationships we have in these equations up here, okay? And again, I have a video working with these equations, so go watch them, okay? Now, when we get two waves, we can have a moving wave, right, and another moving wave. And these two waves, they can, I'm trying to do this is harder than it looks. This wave and this wave, right, they're going to interact, okay? They can move. If I have two waves coming towards each other, they can interact. There we go. or if I have a wave moving really slow and this one's moving really fast, it could catch it and they can interact that way. So there's a lot of different ways that moving waves can interact. And that's what we're talking about. So we know how to describe a moving wave, an individual moving wave, right? Now we want to see what happens when we get two individual moving waves and how they interact with each other. So this is kind of showing you what's happening, right? We have two individual waves. You can imagine that purple wave right there is moving that way, and this green wave is moving that way. So they're going to combine. And when they combine, we're going to get a new wave that's not going to be the frequency or amplitude of either of those waves, because we're going to get some combinations. So first of all, we want to know the difference of the types of waves. In this class, we're going to be dealing with coherent waves. We're not going to really deal with incoherent waves. The coherent waves are where the phase difference is constant. You may be asking yourself, well, what the heck is a phase difference, Carl? Well, phase difference is how much one wave is ahead of the other. So if one wave stays ahead of the other with the same amount, right, which is just like pretty much what we consider a periodic wave, then that's what's considered a coherent wave. But if the waves have a different phase difference, so really what we're saying, if the two waves are oscillate, right, have different frequencies or something like that, they're incoherent. So coherent waves typically have the same frequency and everything, so they're typically coming from the same source. Incoherent waves can be coming from two different sources, and those phase differences are constant. So again, there's two different types of waves. That's all I'm trying to talk about right here, coherent and incoherent. Both types of waves can interact. We can have coherent waves interact, we can have incoherent waves interact. In this class, because we're keeping it simple, we're only going to talk about coherent waves interacting. All these waves that are interacting are coherent waves. Alrighty, I know like here, I'm just showing an example because this is like two incoherent, these are incoherent waves, but when we have to deal with the application, they're going to be coherent waves, which is what's going on here. Alright? So, when waves interact, right, when they combine, they share the same position. When they're, right, at any point, they're sharing a certain position. That's what we call superposition. When two waves are at the same point, we call that superposition. They're sharing the same two different waves, right? The green wave was heading this way, this purple wave is heading this way, but right at that moment, they share the same position, right? And so they have a superposition. That's what we call that, okay? When two waves have a superposition that have the amplitude in the same direction, we call that constructive interference. And those amplitudes, they're going to combine to form a larger amplitude. It's just going to be these two amplitudes together, right? So these two are going to combine to form a larger amplitude. That's what we call constructive interference, all right? And again, it happens when waves share superposition or at the same point. We can also have deconstructive interference, right, where the amplitudes combine to make a smaller amplitude. So this amplitude is smaller than the original, right? Because this, since these are opposite, this amplitude is going to take away from the amount of amplitude that's here, leaving us when these waves combine with a wave that's smaller than this larger one, right? So that's the idea. Constructive interference, these two waves combine to get a larger one. Destructive interference, these two waves combine to get a smaller one. And if these two amplitudes are equal, if this green one was the same amplitude as this purple one, there'd be no wave. They'd cancel themselves out, and that's what happens when we get like these nodes. Okay, there's complete destructive interference, all right? So the way that we can look at these things, because the waves, right, when they're interacting, they're going to have a path length difference, okay? And just to understand, a path length difference is just the difference is the length, the distance that the waves are traveling. Okay, so some waves may have a difference in path length, some waves may not have a difference in path length, right? But we can kind of look at that relationship and kind of understand what it's telling us. So if we look at the difference in path length, where that change in L is L2 minus L1. So the length of one wave, right, or the distance one wave traveled is minus the distance the other wave has to travel, okay? When you get that distance, a change in L, when that change in L, this equation equals to these integers, like 2 times lambda, just lambda, 3 times lambda, 4 times lambda. When that change in L is equal to these whole integers, that's how we know we're getting constructive interference. So you might not know if you're getting constructive interference. You might say, well, I don't know, I have these two different waves. Are they going to constructively interfere when they meet, or are they going to deconstructively interfere when they meet? Well, how do you know? You look at their path length difference. You get their path length difference. If you get, you know, a number here like 2 lambda, or you get a number like 3 lambda, or just lambda, we're telling you that you're getting 2 whole wavelengths, 3 whole wavelengths. You're getting a whole wavelength, so you're getting constructive interference. Versus at the path length difference, right? That the length traveled by one wave minus the length traveled by another wave is equal to something like 2/3 lambda, 3/4 lambda, half lambda. That's where we know there's been constructive interference. So that's how you can decide, hey, I have these 2 waves. What's their path length difference? You figure out their path length difference, you'll understand that they're going to constructively or deconstructively interfere based off of the number that you get. Okay? So that's the idea here. That's how you use path length difference to understand, okay, are these going to constructively interfere or deconstructively interfere, or how you read that equation. If you do this math and you get whole integers of wavelength, you know you've got a constructive interference. If you get, you know, these fraction integers, right, half a wavelength, 3/4 you know that you're getting deconstructive interference. So that's all that's telling us, okay? We can also get the actual number of the amplitudes when they combine. So when there's constructive interference, right, if there is constructive interference, if we've decided that, right, we can see, hey, well, what is the new amplitude of the new wave once they combine? Well, you get it this way, where it's a squared, the new amplitude, this is the new amplitude, is equal to the amplitude of the first one squared plus the amplitude of the second one squared plus 2 times the amplitude of the first one times the amplitude of the second one. So that gets you the amplitude, the new amplitude of the combined wave, okay? The other thing that we're going to talk about a lot over here is that these waves, when anything's oscillating, not just a rope, when you're oscillating, anything's oscillating, that means the thing has energy that it didn't have. Like if I'm just sitting, like not oscillating, I have less energy than if I were to oscillate. The more and more I oscillate, this probably looks really weird. The more and more I oscillate, the more and more energy I have. Okay, and that's the idea. And that's why we have to also talk about intensity. We talk about intensity here because these waves have energy. Okay, they have energy, and do keep in mind that intensity is just the average power. So it's the rate of power, how much power that wave is going to have. So we can look at the energy, how intense that wave is going to be after they combine by using this equation. So it would be the intensity from the first wave plus the intensity from the second wave plus 2 times the square root of the intensity of the first wave plus 4 times the intensity of the second wave. That's how you would get the intensity if you needed it, right? They might say, well, how much power does that wave have? Well, if you know the intensity is just equal to power over time, so you could figure out the power if you needed to, okay? So just keep that in mind. We can find out the amplitude of the wave and we can find out the intensity of the wave. When we're talking about the amplitude, we're talking about how large of a wave it's making. When we're talking about the intensity, we're talking about the power associated, the energy. Remember, powers just work, okay? So we're talking about the energy that wave has, all right? And then with deconstructive interference, we can find the amplitude for the resulting wave when they deconstructively interfere the same way we did up here, but it's slightly different, where it's a squared, the amplitude of the new wave, is equal to the a squared of the first wave plus the a squared of the second wave minus now 2 times the amplitude of the first wave times the amplitude of the second wave. Okay, and again, intensity, we can get intensity of this new wave through deconstructive interference, where the equation looks almost the same, where the intensity is equal to the intensity of the first wave plus the intensity of the second wave minus 2 times the square root of the intensity of the first wave times the intensity of the second wave. And again, amplitude's how large the wave, how high the wave's getting. Intensity is how much power, how much energy is going to be associated with the wave, so we can find that out. All right? Now, that's how we get amplitudes of the resulting wave. That's how we get intensities of the resulting wave. But what if we just want to write an equation for these 2 waves combining? An equation for this, we'll say the green one's moving that way and the purple one's moving this way. What if we want an equation to describe this whole thing together? Well, that's what this is doing. Okay, so if we got to describe those two waves, right, we know that that plus and minus is just dictating the direction it's moving. So one of the waves, right, is moving to the right. One of the waves is moving to the left. The green one's moving to the right. So that's what this is describing. Okay, this purple one's moving to the left, and that's what this one's describing. That's what this part's describing. If we don't know, we clearly could tell by what x is saying. If x is positive, that must be talking about a wave moving to the left. If x is negative, that's talking about a wave moving to the right. So these are talking about two different waves interacting, two different sine waves interacting, okay? So that's trying to describe these two waves when they're coming together. Once they come together, they're going to go through constructive and deconstructive interference, a thing we just talked about, right? But it's a lot more complicated than this picture. All these amplitudes are just going to combine and deconstruct and construct with themselves and give us a new wave, okay? That new wave is what we call a standing wave, and that standing wave can be described with this equation, okay? So again, if you have to give us this equation, I don't see the professors really having you use this equation. Just be aware of what they are and what they're telling you, okay? So this is talking about the two different waves, right? It's describing this is one wave, this is another wave combining. This is talking about the wave once it's combined, right? So this is this equation is for this wave. If you wanted to describe this wave, which is again a result of these combining waves, or if you just want to describe this situation, these two waves combining before we look at constructive and deconstructive interference, you would do it this way. Where again, omega is angular frequency, k is wave number in both of these equations. All right. So, what is the point of all that? Well, it's about looking at being able to determine the wavelengths and frequencies of any system. We can look at strings on a rope, but we can look at any system, because this idea here that we have here is true for anything. It's true for you. It's true for bridges, any object, right? We can look at we can find the wavelength of any object by knowing the length of it. So your wavelength, how a wave's going to set up on you, is based off how tall you are, the length of your body. Okay. The wavelengths that are going to set up on a bridge is based off how long that bridge is. That's what this is saying. So wavelengths are directly related to the length of the system, or the original length of the system. And we know that the frequency is related to the wavelength, right? And so that's what this is saying. So if we want to know the wavelength for any system, okay, we just have to know the original length of that system, and we can get it, okay? This n we'll talk about in a second, all right? Which is just, all we're doing is rearranging this equation, and there it is. So there's the wavelength for any system, okay? Where n, we can look at how many nodes or antinodes, and that can function in and out, okay? But this is just generically to find the wavelength and frequency of any system. These are the fundamental equations, okay? So this is just this equation rewritten, and then once we know the wavelength of any system, we can use this equation to find the frequency of that system based off that wavelength that we see there. Okay, but this gets a little bit deeper, okay? There's more to it than this, okay? So what we know is that all systems have a natural frequency that they oscillate at, okay? Like if I start to put energy into a rope, I might not get that rope to, it might not oscillate. I might not get any oscillation, any wavelength in it, because the amount of energy that I'm putting into it, or the frequency that I'm oscillating, it might not be enough, okay? Because every system has these fundamental frequencies and that's what we consider the lowest frequency that they can oscillate at. Okay, so the first thing to realize is that every system has a natural frequency to them, or a natural wavelength, and that natural wavelength is based off their length. And because they have a natural wavelength, they're going to have a natural frequency to them. They're going to resonate or oscillate. a certain frequency. Okay? Now, the fundamental frequency is the first frequency for any system. Okay? It's the what we call the lowest resonance frequency. We're going to talk about resonance here in a second. But another way to say it is it's the lowest natural frequency. So you can say this is lowest fundamental frequency or lowest natural frequency. The lowest frequency that this system can oscillate on. So you're going to have to jiggle it a certain amount. There's going to have to be a frequency that you're going to have to, or a certain amount of energy that you're going to have to put into the system before you can start to get wavelengths in them. That's what we're saying. So the lowest frequency that you have to oscillate something at is called the fundamental frequency. Okay. Now mass spring systems, they only have one fundamental frequency. Okay. So there's only one frequency really that those mass spring systems will oscillate on. But strings and pipes, they have several resonance frequencies. But when we start to talk about those other resonance frequencies, we start to talk about them in terms of harmonics. But when we use the word harmonics, just keep in mind that it's just the integer multiples of fundamental frequency. So it's just, right, we have multiple integers of that fundamental frequency. That's all harmonics are, but that fundamental frequency is really just determining all those different harmonics. These are different resonance frequencies for a rope on a string, but we could also say that those are different. This is the fundamental frequency for the string. These are also fundamental frequencies of the string, but instead of calling these fundamental frequencies as well, we would call these are harmonics of the fundamental frequency. So we have the fundamental frequency, the lowest frequency that this system's going to oscillate on to give us some sort of wavelength, right? And then if there's multiples, if we can have multiple frequencies that give us multiple different types of wavelengths, then we call those harmonics. So mass spring systems, they only have one fundamental frequency. Strings in a pipe, they have several fundamental frequencies, but instead of calling them multiple fundamental frequencies, there's just really one fundamental frequency, and the rest of these are just called harmonics, okay? So when we have to find that fundamental frequency, there's a definition of fundamental frequency. There's a reason why this is considered fundamental frequency, because fundamental frequency is always when n equals 1. So this n in these equations is considered the antinode. Okay, well what the heck's an antinode? Well, when we have a rope on a string and we do start to oscillate it with enough energy and it starts to create a wave in it, that wave can be reflected back if it's interacting with some like a hard boundary. So if I have a rope and I attach it to this wall, that's considered a hard boundary. The reason why it's considered a hard boundary is because as I oscillate the wave is moving through air, and when it gets to the wall, if the wave were to continue, it would have to oscillate through this hard barrier, and it can't do that, right? But let's say that I, for some reason, had a rope inside the wall, and I was able to jiggle it. So I'm jiggling the rope, and the rope is jiggling in the wall, and then all of a sudden the rope comes out of the wall. There's not going to be this reflection, since we're going from a hard boundary into a soft boundary. So you only get this reflection when you go from soft boundaries to hard boundaries, when you go from the wave moving through the air into the wall. But if you're moving through the wall into the air, you don't get this, okay? So that's just important to understand why this is setting up. But if I do have a rope, and I do have it tied on both ends, which would be no different than me holding one end of the rope and tying it to one end of the wall, and I start to oscillate it, the wall, or the two ends, will work as hard barriers. And so what starts to happen is as I oscillate this rope, I get what we call an incident wave. That's the initial wave. Once it hits the hard barrier, it's going to reflect. And when it reflects, it switches, so the amplitude goes opposite, and then it starts to move in the opposite direction that it was moving originally. So the incident wave is moving one way, right? And the reflected wave is moving the opposite way with opposite amplitude. Okay? When you have these open spaces like this, between the reflected and incident wave, we call those antinodes. These places in between where there's total deconstructive interference, we call those nodes. Okay? So this N up here is the antinode. It's how many bubbles. It's the bubbles that are formed you can think of. Right? Here there's one antinode. Okay? Here there's 4 antinodes. And 1, 2, 3, 4, 5 nodes. Remember the nodes are these parts in here. Okay? And these 2 N ones are also considered nodes. Okay? So keep that in mind. Alright? So with fundamental frequency, N is equal to 1. So when we're saying that, keep in mind we're saying that N is an antinode, so you only have 1 antinode and 2 nodes essentially. That's the only thing that's essentially the fundamental frequency. Like I said, everything's are harmonics of the fundamental frequency, but you can call these fundamental frequencies if you want to. We kind of go back and forth in physics. All right? Now, besides the fundamental frequency, if we need to find any of these other frequencies, right, these harmonic frequencies that go along with these other fundamental frequencies, which are just integers of the original fundamental frequency, we can use this equation to find those other frequencies, okay? We can use these equations to find the wavelengths, which is what I did over here, and then we can use this equation to find the frequencies that are associated with those wavelengths. Where again, V in here is going to be the speed. It's the speed of the wave. I forgot to write that. So V is speed of wave. N, we already said, is antinode. L is original length of system. Okay? So you can find any of these other harmonic frequencies or other fundamental frequencies of, again, the only thing that doesn't have it is mass spring on a mass spring system. So pipes, air running through pipes, strings, these types of things. You can find those different resonance frequencies or those harmonic frequencies using this equation right here. Okay, so just keep that in mind that there's 2 different ways to find frequency. This is for the fundamental, specifically for that first one with the lowest resonance frequency, or the lowest natural frequency. This can be resonance or natural. It might be better to have natural in your head, because resonance means something, but fundamental frequency is a resonance frequency. So the lowest natural frequency or the lowest frequency that the system naturally will oscillate at, or the resonance frequency. That's what this equation gets you. If you gotta get any other ones, that's what this equation gets you, okay? But keep in mind that there's frequencies in between here and here. There's frequencies in between here, right? Like if I have a motor that's oscillating this rope, I have to adjust it to a certain frequency to get here. Just because I turn the motor up one level of magnitude doesn't mean it comes here. This is associated with a very specific frequency as well. Okay? So that's super, 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 super important to keep in mind. Okay? And also keep in mind that this is the equation we're starting with over here. I think I forgot to mention that. This 2L is just coming from this. Lambda is equal to 2L for this fundamental frequency. So we replace that in this equation, and that's how we get this. Do keep that in mind, okay? So we are using lambda for fundamental frequencies. Lambda is equal to 2L. So that's why this equation is written the way it is. So there's certain frequencies that get you these, but there's also frequencies in between those, okay, that we can give to the string. But when the string, like if this is a rope, again, that we're jiggling, the frequencies in between these two, they're going to be chaotic. They're not going to give us these nice little pictures that we get here, where these specific frequencies let this rope set up in a very specific way. And when it does this, that's where we have the maximum energy in the system. So what in the heck does that mean? What in the heck is Carl talking about there? That's where we get into this idea of resonance, okay? So resonance starts with this idea of forced oscillations, driven oscillations. Like I said, I attach a motor to this rope. That motor is driving the oscillations for this. Or let's say I have a bridge, and there's wind hitting the bridge. Right? That wind can be seen as a driving force. Okay, and if that driving force, if the frequency of that driving force matches the fundamental frequency of, let's say, a bridge, those things are going to start to oscillate together, and that bridge will start to oscillate with maximum amplitude because the driving force is going to match the resonance frequency of the system, and it's going to make it oscillate with this maximum energy, which is what's happening with all these. Okay, so that's the idea, okay? Resonance is based off of forced oscillations. Forced oscillations are usually coming from some outside system. Like we can attach a motor to a rope and jiggle it. My hand, when I start to shake a rope, that is the driving force in that case. So it doesn't have to be a machine, but if it's some outside force, right, that's acting on the system, all right, that's when we start to see resonance. But resonance will only occur when the driving force matches the natural fundamental frequency of the system. Okay? When that happens, we get resonance. So that's what all this is saying. Let me make sure you see these separate things, because these are all concepts here. Okay? So when the driving force matches the natural or fundamental frequency, like I said, you can think of this as natural frequency or fundamental, which is what I'm saying here. When the driving force matches the natural or fundamental frequency of the system, that's when we get resonance, okay? When systems resonate, the amplitude becomes maximum. That's what I just said. So like when the bridge starts to resonate with the wind, and if the wind matches the frequency of the bridge will start to sway really large. Start to have very large oscillation, okay? All right, and keep in mind, when this amplitude is max, we're saying that the energy of that oscillation is maximum. Remember, these oscillations, the only reason why things are oscillating is because the system has energy. The energy is causing it to oscillate, okay? So the more energy a system has, the higher the frequency, the smaller the wavelength, and vice versa. The less energy a system has, the lower the frequency, and the larger the wavelength, okay? That's how they associate, okay? But it's, again, the idea is about resonance, all right? So when we get certain frequencies, so this string is going to have a certain length to it on its own, right? And this string is going to have a certain fundamental frequency that's going to naturally oscillate on that. It's going to have a natural frequency that it'll oscillate at, right? So if that driving force, if we can get a motor, like the motor that we attach to this rope, if we can match the frequency of that motor to the natural frequency of this rope, we start to get the string starts to set up in certain ways. So with that, when we resonate with the fundamental frequency or that natural frequency, we get this situation where we don't get a full wavelength. We see that when we're using this equation, again, n is equal to 1 here, so when we put 1 in here, we see that the length of the rope is equal to half a wavelength, which is true. Because we know a full wavelength would be a full wave. So we see right now that the full length of the rope is actually equal to half a wavelength. Or if we use this equation and use n as 1, we see that the wavelength is equal to twice the length. So if I were to get a full wavelength, remember, a full wavelength is it can be looked at as crest to crest, or it can be looked at as this point to this point, okay? So we know if we were to get another wave, we would get a full wavelength, but here we just have half a wavelength, okay? How do we know? How do we get those equations? Again, by using these, making n equal to the amount of antinodes here. I have one antinode, okay? So for this first fundamental frequency, this is the fundamental frequency, or for the first frequency, resonance frequency, this is what we get, okay? But this is also considered the fundamental. These are integers of the fundamental. What we like to refer to these other ones as harmonics, but they're just integers of the fundamental, okay? So, what happens when we go up to the next frequency, right? Which gives us this situation, which gives us 2 antinodes and 3 nodes. Well, we can see first by using this equation that yes, the length of the rope, okay, this is important to see, is now equal to 1 wavelength, right? If we follow this, we see that now that's 1 full wavelength, right? That's 1 wave, 1 full wave. So then that's what this is telling us. The length of the rope is now equal to 1 wavelength. The wavelength is equal to the full length of the rope. Okay, how did we get that? We just put this n equals 2 into these equations, and that's how we get it. So again, how do you get the wavelength of these systems? You use this equation. You put the number of antinodes into this equation based off what we've given you, and you can get the wavelength. Once you have the wavelength, you can then find the frequency that gives you 2 antinodes, that gives you 3 antinodes, that gives you 4 antinodes. Or a better way to say is you can find the harmonic frequencies of this rope, where you can find the multiple integers of the fundamental frequency of this rope, okay? All right, so, all right, if the next harmonic frequency that we get to up to, remember there's frequencies in between these two, but once we match the next harmonic or the next frequency, so when we say integers of frequencies, we're saying that the first fundamental frequency is equal to f, the next fundamental frequency is equal to 2f, the next the fundamental frequency after that is equal to 3f, okay? And those integers are really just coming from here, okay? Because those are the integers we're putting in here. So, right, so for the net, right, this is f, this is 2f, this would be 3f, okay? So for the next harmonic frequency that gives us this, right, we see that n is equals 3, so now we see that the length of the rope is equal to 3 halves of the wavelength, or the wavelength is equal to 2/3 of the original length of the rope, right? And based off of the wavelength, we can figure out, again, putting that wavelength into this equation, getting this, we can find out the frequency that's associated with that specific harmonic of the wave. So, and then for the last one, again, just trying to beat a dead horse here, but here we see that we have 1, 2, 3, 4 antinodes and 1, 2, 3, 4, 5 nodes. We're always ignoring the nodes. The antinodes are the only thing we need for the frequency, the length, and the wavelength equation. So again, if we wanted to look at length, we can see now the length is equal to 2 wavelengths, right? Where this is 1 wavelength, and there's the second one, right? There's 2 wavelengths in here, and we see that the length of the rope is equal to 2 wavelengths. That's what it's telling us. Or, right, a wavelength is equal to now 1 wavelength. We see that this is 1 wavelength, right? Again, it's going to make a second one when we get all the way to the end, but 1 wavelength is equal to half the length of the rope, because here we have 2 wavelengths in terms of the length of the rope. So that's telling us the wavelength at that certain frequency. So we might give you frequency, and you can find out what the wavelength of the rope is, right? You can go back and forth. But the idea here is that it's about energy, okay? So resonance frequencies occur when we give a specific amount of energy to the rope, okay? If we don't have that specific amount of energy in the rope, this won't happen. That starts to correlate into quantum mechanics. Okay, this is your first idea into quantum mechanics, and that's what quantum mechanics is saying, is that there's no in between, right? You either get this or this. Okay, there's only one frequency associated with this wavelength. There's only one frequency associated with this wavelength, right? There's nothing in between, and that's essentially what quantum mechanics is saying. Is we just get these quantum numbers, this one value associated with this one wavelength. Okay, so this is essentially trying to get you there. It's not quite saying that. What we want you to do is take this idea into sound, okay? Because when you start to oscillate the air in an oboe, right, or a clarinet, or saxophone, right, you start to pick up on the resonance frequencies. And the nice thing about like the oboes or saxophones, or even this right here is giving you an example of like a violin or guitar. When we want to change the sounds, right, because we can tell that if I could strum the string fast enough, eventually I'm going to get a higher sound, but we can't strum the guitar string that fast. So what's the other thing that we could do to change the frequency? Right? The frequency is the hertz, right? The thing that your ear's picking up on. You change the length, right? So with the guitar string, when you press down on a fret up here, the guitar's one length. But when you press down on a fret over here, the guitar's another length, and you get two different frequencies based off the length. And the sound that you're getting off of those different lengths, those are all the fundamental frequencies. So for every fret, right, you change the length of the guitar, every length has its own fundamental frequency associated with it. All right, so those are the sounds that you're getting. And the same thing with like a saxophone or a clarinet or something. When you close certain valves on the saxophone or something like this, you're changing the length of the tube, okay? When in sound, we talk about how open-ended tubes and closed-ended tubes also affect the sound. So that's not here. But that's what starts to happen. We change the length of the tube by opening and closing those valves. The different lengths then associate with different frequencies, and those frequencies are what we hear. That's what gives those instruments notes. Even if you start to, I'm sure in class they give you the demonstration where this rope is hooked up to a motor. As we turn on that motor, what do you hear? It goes, that's telling you something. This lowest, the fundamental frequency is going to be the lowest frequency. It's going to be the lowest sound as well that you would hear, right? And as you increase in frequency, you get higher and higher. Okay, that's the idea to think about here, because that's what's happening. So this does give off a lower sound. Why? Because it's a lower frequency. There's less energy. All right, well, I hope this was helpful. I know there was a lot here, but keep in mind what we said. Keep in mind what we're trying to say with fundamental frequency, how fundamental frequency associates with oscillation and resonance, right? Versus just looking at constructive and deconstructive interference of how waves interact, all right? I am super proud of you. You have gone so far and you've made it to the end of physics, and I really, really, really hope that you're patting yourself on the back, because this isn't easy. You did it. So I'm proud of you. And I just cannot wait to see the things that you are going to do in your life. You're going to change things. You're going to change your life. You're going to change people's lives. And I just think that is just so amazing. That's why I do what I do. Because the things you guys are going to go off and do just gets me so excited. Because all of you are just amazing people that, you know, no matter what's going on, you guys do want to change the world. You want to affect the world. You want to make it better. I just think that's awesome. So I'm super proud of you all. Way to make it to the end of Physics 1. If you have to take Physics 2, you're going to have a lot of fun. All right? That's it for this video. Have a good one, and I'll see you on the next.